make sure that all these wires are connected up correctly. Got a spaghetti junction in here. Good job these are all coloured, otherwise I wouldn't know which wire was meant to go where. I think this could do with a little illumination. Use this light from my photo developing lab. Oh, hang on. Now I can't see half the colours. Some have even turned to black. And what will happen if I take the red filter off?
That's interesting. I can only see some colours under the red light, but all of them under the white light.
It's better. Oh, wouldn't you know it? Science line. Sometimes I think I'll never get my work finished. Hi, what's going on?
Stella, we've been wondering, why is the sky blue?
Is it because it's reflecting the sea? The sea's blue?
Also, why is the sun yellow?
It must be because it's made up of burning gases. And fire's yellow.
And why are sunsets red and orange?
And why do we never see green in the sky?
I'm onto it. This all comes down to light. And I think it's time we generated some light of our own. Now, this light is travelling through air. And when it reaches the block, it's travelling through glass. It's all fairly straightforward. But what happens if I change the angle at which the light hits the glass? The light changes direction. This is refraction, and it happens because the light slows down as it enters the glass. Now, if I pass the light through a prism, it's refracted. Something else happens. White light entering the prism, but all these colours coming out. Well, this is dispersion. And what we're actually seeing is what makes up white light, all the colours of the rainbow. And this is why the sky is blue and a sunset is orange. But I think Femi should look into all of this a bit more.
Gorgeous, isn't it? Bright summer's day, clear blue sky and a bright yellow sun. But why? I mean, we're all used to these colours. But why is the sky blue? If I wasn't enjoying myself so much, it's the sort of thing I could investigate.
Perhaps I could help you there.
Well, what do you know? It's Ian McCaskill, the top weather forecaster.
So, Ian, why is the sky blue?
Well, it's all to do with the fact that the sun produces white light, but that our atmosphere is full of stuff and much denser than space.
Well, I understand about the sun producing light and the Earth's atmosphere being quite thick. What's that to do with colour?
Let me show you. I've filled this tank with water, and I'm going to put this milk powder in it, and this will represent our atmosphere. It's actually quite a good representation of the atmosphere, because the milk powder represents all the water droplets, all the dust, all the pollen, and all the other particles in the atmosphere. And this is our sun, producing nice white light, just like it does in space. The sunlight in space is white. Now, if I lower the sunlight into our atmosphere, you'll see what happens.
Oh, yes. Well, the light around the beam appears to be blue.
Right.
And if I look round into the end of the tank, well, the sun's light, it looks yellow.
Well, yes, that's because, as you know, white light is made up of all the colours in our spectrum. Now, all these colours get pushed about by our atmosphere, and it just so happens that the blue light is the one that's scattered most of all. And so when you shine a white light into the atmosphere, all the blue light is scattered all over the place, all over the sky, in fact. And of course, when you take the blue colours away from the sunlight, you're left with a yellowish looking mixture, and that's why the sun looks yellow.
So if you take away some of the colours that make up white light, you get a new colour. In this case, taking away the blue leaves yellow as the predominant colour, giving the yellow colour of the sun.
OK then, Ian, but the sun doesn't just look yellow, because in the late evening when it's setting, it can look red. Now, what's going on there? Is it more blue light being scattered, maybe?
Yes, more blue light is being scattered, but something else is happening. As the sun starts to set and lowers, the light has to travel farther and farther through the atmosphere, and that, of course, means...
Well, even more stuff or more particles for the light to travel through.
Exactly, and I can get the same result by adding yet more note powder to our sky. Here goes.
As the sun travels through more of the atmosphere, even more blue is scattered, making the sun's light more orangey. Then some of the yellows are absorbed by the atmosphere, and when you take the blues and the yellows away from white light, you're left with a red colour, and that's why the sun, just as it sets, appears red.
OK, so that leaves us with the red, but it also leaves us with green. Now, I have seen some very red sunsets, but I have never seen a green sunset.
It does happen sometimes if you're very, very lucky. Normally, of course, the red light is so strong that you don't even notice the green. But if you're in the right place at the right time, something fantastic happens. Just as the red is dipping below the horizon, there's only green left, and that's called the green flash. It only lasts about a second, and it's easier to see from space than Earth, but it does happen.
And a very lucky scientist in America managed to film it. So as you can see, all the fantastic colours that make up the sky happen because the sun produces white light.
Sounds as if there's a party going on.
Hello? Stella, we've got another problem for you. Why do our T-shirts keep changing colour?
My white one changes with whatever colour signs on it. It looks red under red light, green under green light, and blue under blue light.
My red shirt goes black under green light. And my cyan shirt goes green under green light, blue under blue light, but black under red.
Maybe it's because red, green and blue are all dark colours, and when you mix them together, you get an even darker colour.
Yeah, like mixing dark paints together. You get a sort of browny black colour.
What's going on, Stella?
Enjoy your party. I'll get back to you. We can only see anything because light falls on its surface. What happens when light reaches this surface? It's stopped or absorbed. With this glass, it's allowed through. And with this mirror ball, it's reflected back. White light is made up of all the colours of the rainbow, but I'm just going to use the primary colours, blue, green and red, to make it easier for you to see what's going on. If we shine our white light on different coloured objects, look what happens.
A red object absorbs all the colours of the spectrum except for red, which is reflected. We can show this if I turn the cube to this special side. It's a similar story with this green side. All the colours are absorbed except green.
I think Femi should find out more.
I'm off to do another investigation, but first I need to get some shopping in. See you shortly. Look at this scratch. Now, this red paint must have come off the car that did it. But which car? Let me think.
There were loads of cars and they were all red. So I'm going to make it my investigation to find out which one's responsible.
And I know just the person to help me do it.
I'm off to see forensic scientist Dr. Peter Sansom, who can use colour to catch criminals and people who scrape against my lovely car.
I have a sample of the car that scraped mine. As far as I'm concerned, it's just some red paint, and my car was surrounded by 5 red cars. How can it tell you anything?
Well, when you look at red paints, there are lots of different shades. I mean, you look around at different cars and you see probably those 5 all had different shades. And even if they look exactly the same, when you look at the way that the paint is actually reflecting the light, you'll probably find that one red has got a bit more blue in it and the other red is more orangey.
Peter can use a special machine to measure how different colours reflect white light, which of course is made up of all the colours in the visible spectrum. A blue paint, for example, mainly reflects the blue part of the spectrum, whereas a red paint will mainly reflect the red part of the spectrum.
Your problem is slightly different. You've got different reds. So let's take these 3 greens and they look almost exactly the same. Yeah?
Yep.
But when we look at the spectra of those, we find that actually they differ quite a lot. And you can see that this one reflects more red. This one is reflecting a little bit of blue here, whereas this one is a mixture of colours being reflected so that we perceive green.
So even 3 colours that look quite pure, for example these greens, are in fact reflecting different mixtures of colours, including some you wouldn't expect to see. And forensic scientists can use these colour fingerprints to match evidence from the scene of a crime with examples of all the paint colours they hold on file. So I'm getting closer to the person who damaged my car.
Peter,
Oh, yeah.
I have the results. What can it tell us?
Well, first of all, obviously it's a red paint, but the actual measurements of the colours seem to suggest that the nearest one we're going to find like it is a Ford. Hang on a moment. Yes, a rather recent Ford seems to be the most likely paint for this.
Excellent. A red Ford.
Hang on a moment. That's not sufficient for evidence. That's an indication.
Peter, don't worry. It's enough evidence for me. I know exactly who that Ford belongs to. Thank you.
OK.
A red Ford. Hang on a minute. You've got a red Ford, haven't you? No, you've got a red Ford. And you were parked in the car park earlier. That car belongs to you, doesn't it? You owe me for that car. I can't believe you made me go through that entire investigation, and it was you! You just come back here and own up to it!
Right, gonna need some new wire. So, objects reflect certain colours. But what about this? Now, this is red, but it's a light, so there isn't any reflection involved. The light is passing through this red filter. Now, what do you think this filter's doing? I think we need a bigger example. If I put in a red filter, only red passes through. The rest of the colours are stopped or absorbed. Green filter, only green passes through. Again, the other colours are absorbed. Now, colour filters are used all the time to great effect. I think it's time Femi investigated.
Stella's given me this strange poem to read. In a hot desert, round a campfire cooking dessert, along came the cold night, and with it such a big fright. Now, she's told me to make it as atmospheric as possible, but I have no stage set, no props. In fact, the only thing she's given me are these. I think I'm going to have to investigate this one a little further.
So I've come to see Philip Craxford, lighting director at the Theatre Museum in London, who says he might be able to help me.
Using coloured light is a fantastic way of creating mood and atmosphere, and people associate their mood with colours. So if you're feeling a bit depressed or a bit down, you might say, I'm feeling a bit blue. Also, we could do something like, if I bring this light on down here, this orange, I could shine it on you and mimic something that happens in the real world. In this case, something like a fire, sitting next to a roaring log fire.
Now, that is very cosy. Do you think you can help me out with my poem, help me jazz up the reading a bit?
Absolutely, we can add some real colour to that.
And this is where the colour filters Stella gave me come into play.
By using these filters, we can get any colour we want. If I was to use coloured light bulbs, I'd be stuck with just the one colour. Using these, I can get lots and lots of colours.
OK, so how exactly do they work?
OK, remember again, white light contains all the other colours of the spectrum. With this filter, it allows some of the colours to pass through, and it stops other colours. It's the colours it allows to pass are the colours you see.
Phil, thank you for these. They're great. They'll make a brilliant impression on my poem. I wanted to ask you something, though. Can you actually only use the colours that you have gels for? What about if you wanted to use a colour and you didn't have a filter for it?
Well, yeah, we can mix the colours if we want to. Take a look at that mannequin over there. We can light it in a blue gel, we can light it in a red gel, or if we mix the red and the blue, we get purple. In the same way, if we mix blue with green, we get another colour. If we mix all three together, we get white. Red, green and blue are the primary colours in white light.
So time to decide which colours to use for Stella's poem.
I often think about the colour red. So maybe we could use this red filter to create that mood.
Well, we could do. Or we could use something like an orangey yellowy red, something like this, to give the effect of the hot sun in the desert.
Yep. OK, finally, and with it such a big fright. OK, green slime monsters, gotta be the green gel, yeah?
Yes, why not?
Scary! In a hot desert, round a campfire cooking dessert, along came the cold night, and with it such a big fright.
Give that woman an Oscar.
OK, let's have another look at your T-shirt problem. I hope you're not all parted out. First, white T-shirt under white light. What colours are being reflected back to us?
Well, white. That's all the colours in the spectrum being reflected.
If I put in a red filter, T-shirt looks red.
The red filter's stopping all the other colours and just letting red through.
And white will reflect all colours.
So the white T-shirt looks red because that's all that's left to reflect.
And it's the same with the blue filter. And it's the same with the green filter. Let's look at the cyan shirt. If I put it in just two of the colours, green and blue, which colours reflected back?
Well, cyan's reflecting two colours, green and blue.
Does that mean cyan is two colours mixed up, green and blue?
Yes. And what's happening when I put the cyan just in red light?
Well, it doesn't reflect red, it absorbs it.
So in red light, it won't reflect anything back.
And nothing reflected back means it looks black.
That's it. Now, I've got to finish my wiring, but before I go, here's something for you to think about. Put a few drops of red ink from a pen into warm water. If I look through the water at the white light, it looks red. But if I look with the light behind me, it looks green. So why do you think that's happening?
So the light she's looking at is white light.
So all the colours must have been there from the start.
But when she looks at it behind her, it appears green. So green is the only colour reflected.
So all the other colours pass through the liquid.
But when she looked at it from the other side, it looked red. So red must be the only colour getting through.
Which means all the colours were stopped.
That's it. Easy when you know how.